These are receiver parameters. First is the selectivity. Selectivity is a receiver parameter that is used to measure the ability of the receiver to accept a given band of frequencies and reject all others. For example, with the commercial AM broadcast band, each station's transmitter is allocated a 10 kHz bandwidth. Therefore, for a receiver to select only those frequencies assigned a single channel, the receiver must limit its bandwidth to 10 kHz. If the passband is greater than 10 kHz, more than one channel may be received and demodulated simultaneously. If the passband of a receiver is less than 10 kHz, a portion of the modulating signal information for that channel is rejected or blocked from entering the demodulator and consequently lost. There are several acceptable ways to describe the selectivity of a radio receiver. One common way is to simply give the bandwidth of the receiver at the 3 decibel points. This bandwidth, however, is not necessarily a good means of determining how well the receiver will reject unwanted frequencies. Consequently, it is common to give the receiver bandwidth at two levels of attenuation. For example, 3 decibel and 60 decibel. The ratio of these two bandwidths is called the shape factor and is mathematically expressed as shape factor is equal to the bandwidth 60 decibel below maximum signal level over bandwidth 3 decibel below maximum signal level. Then, percent selective can be calculated by multiplying the shape factor to 100 or by dividing bandwidth actual to bandwidth minimum and multiplying it to 100. Ideally, the bandwidth at the 3 decibel and 60 decibel points would be equal and the shape factor will be equal to 1. This value, of course, is impossible to achieve in a practical circuit. A typical AM broadcast band radio receiver might have a 3 decibel bandwidth of 10 kHz and 60 decibel bandwidth of 20 kHz, giving a shape factor of 2. More expensive and sophisticated satellite, microwave, and two-way radio receivers have shape factors closer to the ideal value of 1. Second is the bandwidth improvement. As stated in the previous videos, the larger the bandwidth is, the more prone to the noise the signal gets. Therefore, if the bandwidth can be reduced, the noise will also be reduced by the same proportion, thus increasing the signal-to-noise power ratio, consequently improving system performance. Bandwidth improvement is the noise reduction ratio achieved by reducing the bandwidth and can be expressed as BI is equal to RF bandwidth over IF bandwidth. Third is noise figure improvement. The corresponding reduction in the noise figure due to the reduction in bandwidth is called noise figure improvement and is expressed mathematically in decibel as NF improvement equals to 10 log bandwidth improvement. Fourth is the sensitivity. The sensitivity of a receiver is the minimum RF signal level that can be detected at the input to the receiver and still produce a usable demodulated information signal. Generally, the signal-to-noise ratio and the power of the signal of the output of the audio section are used to determine the quality of a received signal and whether it is usable. It is also called as the receiver threshold. Fifth is dynamic range. The dynamic range in the receiver is defined as the difference in decibel between the minimum input level necessary to discern a signal and the input level that will overdrive the receiver and produce distortion. In simple terms, dynamic range is the input power range over which the receiver is useful. It is given by the equation dr equals to 10 log of Pmax over Pmin. 6 is fidelity. It is a measure of the ability of a communication system to produce at the output receiver an exact replica of the original source information. Whenever you come across a high-definition speaker and it makes you feel like the singer is singing right just beside you, then that is a high-fidelity device, or hi-fi for short. That is because it can copy the exact replica of the original source, which is the singer's voice. 7 is the insertion loss, or IL. It is a parameter associated with the frequencies that fall within the passband of a filter and is generally defined as the ratio of power transferred to a load with a filter in the circuit to the power transferred to a load without the filter. Because filters are generally constructed from lossy components such as resistors, imperfect capacitors, and even signals that fall within the passband of a filter are attenuated. Typical insertion losses are between a few tenths of a decibel to several decibels. In essence, insertion loss is simply the ratio of the output power of a filter to the input power for frequencies that fall within the filter's passband, and is stated mathematically in decibel as IL is equal to 10 log of P out over P in.